as we discussed in the last lecture, we can plot the amount of stress which was applied. So this could be sigma max, and then you can change the value of R ratio. So, but if you want to plot the SN diagram, this is called SN diagram instead of calling it sigma N diagram, uh, because to have ease in the alphabetical text writing. So basically S is stress and N is the number of cycle. So when you plot sigma max at constant R ratio, for some materials the the stress versus number of cycle curve looks like this. And especially for steels, the curve looks like this, and it appears, so the line becomes flat. So it appears that if you apply a stress lower than this, then the material will fail at infinite number of cycles, meaning that the material will not fail at all. And as I said, usually the tests are done for 10 to the power 7 to 5 into 10 to the power 8 number of cycles. So what has been found is that for other materials there is no stress below which the material can have infinite number of cycles, but for steels and a few other alloys it is possible to have a stress below which, if you apply the stress, it is not possible for the material to fail. And that stress has been called in literature as fatigue limit or endurance limit. So it is also called fatigue limit, meaning that this is the limit beyond which the fatigue loading will not affect the material at all. But there are some important things in this diagram. One important thing is that if your mean stress is 0, meaning that you have a complete reversal of stress. So you have sigma max, and by the same amount you go down in the negative direction of stress. So when sigma max, the mod of sigma max is equal to mod of sigma min, then sigma mean will be 0, right? If this is the case, then usually the diagram is plotted in this way. So you plot sigma max versus n. But if this is not the case, if there is no complete reversal of stress, then the diagram is plotted between the amplitude of the stress versus number of cycles. Sometimes it is delta sigma. So delta sigma will be double of amplitude of stress. So this is amplitude of stress, and delta sigma will be this dimension. Okay. So these are the two different ways of plotting the diagram, and in this diagram also you can have an endurance limit, but in this case you will have an effect of sigma mean value which will not be 0. Okay, so if you don't have complete reversal of cycle, so if this is my stress versus number of cycle axis, then if you have something like this, so the mean stress is here, right, and this is non-zero. So if you have a non-zero mean stress, then mean stress itself will have an effect on this diagram. So if the mean stress for smaller mean stress, you will have higher uh, so let's say I plot two graphs for different values of mean stress. So this is sigma m1 and this is sigma m2, and sigma m2 is greater than sigma m1. So as you increase the mean stress, the amplitude of stress for failure will decrease. Okay, so this is the difference, and there are these two ways of plotting the fatigue data. So now we will talk about another important aspect of fatigue, which is the statistical aspect. So the statistical aspect of fatigue is very important and also very interesting. Statistical aspect of fatigue. So what happens is, for instance, imagine that you're doing several tests to find out, to make the SN diagram. And remember that in SN diagram, the n axis is in log, in logarithmic scale. So it's a semi-log plot. Okay. So imagine that you're doing tests to find out the SN diagram, right? The question is, how will you find out the stress below which the material will not fail? So how will you find out the fatigue limit? How will you do it? So you will take a specimen, right? So you will take a specimen and then you'll put it in the machine and then you will test it. Let us say you're testing it at a stress of very low value, so 100 megapascal, right? So at 100 megapascal, what will happen? So you ran it for 10 to the power 8 number of cycles, let us say, right? So it failed at 10 to the power, exactly at 10 to the power 8 number of cycle, the material failed. Does that mean that this is your fatigue limit? Does it mean that sigma is equal to this and this number of cycle you have reached the fatigue limit? No, it doesn't mean that, because if it was the fatigue limit, then it wouldn't have failed, right? So what can you do now? So you will do another test. So obviously 100 megapascal is not the endurance limit. So what you will do, you will do another test on another specimen, because this specimen has failed. So you will do another test on another specimen at a lower stress, right? And if that doesn't fail, do you know that that is your fatigue limit? So let's say you're doing it at 90 megapascal and 10 to the power 8 number of cycle, it didn't fail. Okay, so would you consider that to be a fatigue limit? You can't, because it may be that the fatigue limit was 95 MPa, and if the stress is lower than that, material is not going to fail. So it is a go no go situation. Okay, it's a pass fail situation. So it is not possible to find out the exact value of fatigue limit by doing an experiment. This is completely impossible. So this is one statistical problem which you have in fatigue. Apart from, so this will result in a problem of finding fatigue limit, right? But apart from that, what else? So only at the end point you will have this problem, but before that also there are statistical aspects. So let me make an SN diagram example. And so this is my sigma max, at a R ratio of, let's say, 0.1, number of cycles in logarithm, and I get a diagram like this. Okay, so I have performed these tests and then I plot these values in this form. Okay, so now the question is, let us think about another important thing here is that in this region, so there will be a value of yield stress of material, right? So let us say this is your sigma naught. So the important and interesting thing in fatigue is that you can break the material even when you are loading the material below yield strength. Okay, so even if the material is in elastic deformation, the material is failing, and we are not talking about brittle materials, we are talking about ductile steels. Okay, we are not talking about at a very low temperature, we are talking about room temperature, even higher temperature, where materials, especially metallic materials, are known to deform in a ductile way. So when the material is ductile and we are applying a stress which is lower than the yield strength, even then material is failing. So in elastic deformation, material is failing. Is that possible? Okay. So that is a question which you should think about, and we will answer it at a later point of time. So, but here what is happening is that the stress is higher than the yield strength, right? So here you have some plastic deformation. And what is happening here is that you take less number of cycle for failure, right? So if you are at higher stress, you need less number of cycle for failure. If you are at lower stress, then you need more number of cycles to failure. Okay, so this is one interesting part in fatigue, that you can break the material even in the elastic stress, even for the elastic stress. So for the stress when the material is deforming elastically, even in that range you can break the material, or the material will fail. Another important aspect which you found out, that the stress into the number of cycle is somehow showing constant because it looks like a hyperbola, right? So if the stress increases, number of cycle decreases, and vice versa is happening. Okay, so that kind of behavior is also visible from this plot. Now coming back to the statistical question, so these are the two things which you should think about at this point of time. One is this, and another is materials are failing, especially metallic materials are failing even at or in elastic uh, domain of deformation. Okay, so when sigma max is less than sigma naught. So think about those things, and then we come back to statistical aspect. So the question is, let us consider this point. What is happening at this point? So number of cycle, let's say, is 1000, and stress, let us say, is 700 megapascal. Okay, so does it mean that when you apply a stress of 700, and let us say that this diagram belongs to uh, so mild steel, okay, so you know the composition of this steel uh, to a very accurate amount. So what happens is that the question is, if you take the same steel, apply the same stress 700 megapascal with a R ratio of 0.1, okay, and mean stress is 0, so complete reversal, and no, mean stress is not 0 because R is positive, So mean stress cannot be 0. So uh, there is no complete reversal. But so what is happening is we are applying stress of 700 megapascal sigma max at a R ratio of 0.1, and it is the same material from which you have discovered this plot. So does it mean that the specimen will break at 1000 cycles? The answer is no, it will not break at 1000. It will also not break at 1001 or 1010 or 950 number of cycles. What can happen is that the material might fail at the same amount of stress. So the material may fail at 1200 number of cycles, it may fail at 800 number of cycles, and it may fail at 2000 number of cycles. Okay. Similarly, let us take this point. So let us say that this is 500 megapascal. So this is not about if we are an elastic region of deformation or plastic region of deformation. It can happen at any point. So let us take here where the stresses are lower than elastic, lower than yield strength. So 500 megapascal, and it takes, let's say, 5000 number of cycles. If I test the same material specimen of same dimension, so I'm changing nothing, I'm also not changing the testing machine, okay, and I take the same material, same specimen, same dimension, same machine, and I do the test at 500 MPa of sigma max at same R ratio. Again, the material may not break at 5000 number of cycles, it may break at 10,000 number of cycles, or 7,000 number of cycles, or 2,000 number of cycles, or 1,000 number of cycles. So not by 50, 100, you can have a difference of 1000 number of cycles also. The point being that fatigue shows a huge scatter. Okay, so even if you have this curve, it wouldn't tell you, you will not be able to predict that material will now fail at this particular number of cycles. Okay, the reason behind this is that fatigue happens for very localized deformation, and the mechanism of fatigue we will learn in next lecture. But the point being, so, and the proof of that fatigue is happening because of highly localized deformation, the evidence of that is this, that even at stresses lower than yield strength, where material is not supposed to deform plastically, the material is still failing. This is the evidence. So why it is failing? Because the deformation is locally plastic at certain places. Okay, so imagine that you have this specimen, and in this specimen you are not making this specimen from a very sophisticated machine. There is no sophisticated machine which can make a specimen perfect from the surface, right? So surface will always be rough, so you might have a little let's say a surface scratch. Okay, so you can have a scratch like that on the surface, and that scratch will cause a localized deformation. Okay, so if you magnify that scratch, it may look like this, right? And we have seen in fracture mechanics that a crack tip, even if it is very shallow, it will increase the stress intensity at the tip of this crack. And we have also seen in the chapter of fracture mechanics that even if, so whatever stress you have applied for a circular hole, so even for a blunt scratch, the stresses can go at least 3 times higher than what you have applied. Okay, so at tip you can have stresses higher than 3 times higher than what you have applied, and this we can get from English expression of stress concentration factor, right? If you remember that equation, so sigma at the tip is usually sigma applied into 1 plus 2a by b, where a is the minor axis and b is the major axis. So for circular case, a will be equal to b, so it will become 2 plus 1 is equal to 3. So you will have 3 times of the applied stress will be felt at the tip of that circular hole. These scratches will be not circular, it will be sharper than that, and as you go sharper, this factor can increase. Okay, so what can happen is that even if the stresses are elastic in the global specimen, at these localized places you can have a very high stress value where you can have plastic deformation. Okay, and what are you doing? You are pulling this and then pushing it back if it is a complete reversal cycle. If it is not, then you are pulling it to 50 megapascal and then you're coming back to, let's say, 15 megapascal. So both are positive and you are applying it in cyclic way. Okay, so what will happen is that here you will have a bigger plastic zone forming, and then you will be decreasing the amount of stress, and this will cause the plastic strain to vary in each cycle, right? And this will cause a highly localized deformation which will lead to failure even at stress lower than the yield strength. So the whole material is not deforming plastically, but localized deformation will result in failure. Okay, so and so this is the mechanism of fatigue, and this is the reason why you have huge scatter in the material. Okay, so the reason is you cannot be sure that how many scratches are there. So when you make two samples, the surface finish of those two samples will be different. Okay, that is one case. Surface finish of two samples cannot be same. Okay, then another reason is that you can have different inhomogeneity. So you can have inclusions inside the material. Okay, you can have carbides, you can have different things which can act as stress raisers inside, and they will give you a localized plastic deformation, and these will vary in different specimens. Okay, and because of this, one sample will break at 1000 number of cycles, probably because there were less number of inclusions or there were less number of scratches on the surface of the specimen, or it can take more than what you got this diagram for, so more than 5000 number of cycles, so it might break at 10,000 number of cycles, because this you removed the scratches from the surface, you made the surface very clean, and also maybe because there were not so many inclusions in that particular piece of material which you took to fabricate your specimen for testing. So each specimen for fatigue will have a different diagram. Each specimen will have different SN diagram of its own. Each specimen will have its own fatigue limit. Okay, so this is the problem with fatigue, because there is a huge scatter involved in this. So the solution has to come from the statistical side, and the solution is that to define the probability of failure of the component. Okay, so what happens is, instead of having one single curve, you will have you will have many curve like this. Okay, and so let me draw one more. So now the middle one, we can actually, you can have many more lines, but what we are doing is we are doing, let's say 1 2 3 4 5 and more than that. So let's say we are doing 10 number of tests at each stress levels. Okay, so we have different stress levels and we are performing many number of tests. Okay, and we are getting obviously different values for the number of cycles for which the materials or the specimens are breaking, because each specimen will have its own fatigue property. Okay, because it will have a unique number of defects in it and unique number of surface defects on it. Okay, so this is like an individual human being who has his or her own personality and diseases and strength, and based on which the whole life of that person is described. So every person is unique, every person is different. No one is smart and no one is non-smart. Everyone has a different problem solving approach. So you give a problem to, let's say, 5 people. All those 5 people will look at that problem in a different way, because those 5 people are different entities and they are unique in their own personality. Their DNA is different, right? So each person will look at that problem in a different way and they will do something, right? So we are not talking about a mathematical problem, because all people will not be able to solve the mathematical problem. So we are talking about a practical problem. Okay, so let's say the problem is that you have to go somewhere and you give the same option to 5 people, and 5 people will take that problem in a different way and they will decide to go in a different way. So some person might uh, choose to go by train, some person might go choose to go by car, some person might choose to go by walking, some person decide some one of those 5 people may decide not to go at all, right? So it's the same thing, but 5 people will be taking different options depending upon their comfort and a lot of other things. Similarly, each specimen will act as an own entity and they will deal with the cyclic loading in their own way, because they have different amount of defects in it and they will fail at different number of cycles. So what you have is you have a probability distribution at every point. Okay, and this has a trend. Okay, the trend is at higher stress level the probability, so the number of cycles range is smaller, and as you go lower in the stress, this range increases to a very great amount and you reach a place where you cannot actually capture the whole probability because it hits that endurance limit value. Okay, so instead of defining one SN curve, what you can do is you can do, let's say, 20 number of tests at each stress level, and then you define some probability and then you plot the probability curve for 50%. So let's say this central line is the line for probability of failure of 50%. So this is the mean of the whole probability curve. Then at the end you can have the boundary limits. So you can have 90% tolerance bound and 1% or 10% tolerance bound. You can also have 1%, but 1% is not good, because you are hitting the extreme and you don't have sufficient amount of, you usually don't have sufficient amount of data to define the lower bound. So so you can have so what you can do is you can do this kind of test, and then if your component is beyond this 90% probability of failure, then you can say that you are safe. Okay, so this is how uh, this is how we deal with the statistical problem of fatigue failure. And again, in fatigue also, the probability equation of Weibel's distribution is generally used. So we have discussed this Weibel distribution when we described about brittle fracture probability, and similarly we use the same. So Weibel's distribution function is simply this. So if you remember that weakest link or weakest chain example, so what you have is uh, sigma minus sigma minimum divided by a scaling factor. So it can be sigma naught minus sigma minimum, and this can have a power n or m or something. Okay, so usually we have this kind of equation for probability distribution. So, and this will have a negative sign inside. So, such kind of probability distribution function can be used for defining the probability of failure in fatigue. And about the mechanism how fatigue failure happens and how fatigue will be causing the deformation in the material when we have a crack in the system, that we will discuss in the next lecture. So far what we have discussed is fatigue, and the end result is failure, of course, but so far we have not considered a deliberate crack in the system. Okay, so this part of fatigue was comparable to tensile testing. The only difference was, in tensile testing you apply a load and you never decrease it, you keep on pulling it. And in this case you apply a load and then you decrease the amount of load, and then you go back up and down again. Okay, so this is the difference. Okay,